Okay, hi everyone. My name is Shasank Chavan, and I manage a development team at Oracle called the In-Memory Database Technologies Group, where we are primarily responsible for creating the in-memory column store solution that we have here at Oracle. And today's talk is going to be the top 5 transformational technologies with Oracle's autonomous database. Okay, so let's go ahead and get started. This is the safe harbor statement. Okay, so let's begin. I always like to begin with this motivation here. So cloud enterprises need autonomous databases now. So what do I mean by that? If you're a company running on the cloud, main thing that you care about as any company is you care about efficiency. You want to stay competitive. You want to be able to operate in real time. And that means, you need to be agile, efficient, and really listen to the data and react quickly. But as you transition to the cloud, other things start to matter. Lower costs. There's a reason why you're moving to the cloud from an on-premise situation here. So you want managed services and IT infrastructure. You want a pay-as-you-go model. You want simplicity. And I give this example that if you want to build a smart home, it's very complex to start piecing together a bunch of different technologies. You really want to go with one integrator and be done with it. And that person's the responsible party here. There's compliance. Sometimes your data has to be kept in a particular geography to comply with government policies. And security and scalability. So there's a bunch of requirements that you have if you're going to transition over to the cloud. Now, the other thing here is you want to eliminate drudgery and save costs. So DBAs spend most of their time on generic tasks. If you look at the picture on the right here, you'll see that the day-to-day administration work is about 34% of the time being spent. Then there's backup and recovery at 14%, tuning the database is 26%, dealing with upgrades and patches 21%. So you see a significant amount of time is spent on these generic tasks, and that really leaves very little time to innovate on your business tasks. And this inefficiency can cost your company, obviously, dollars, lots of money. So that's kind of where cloud enterprises are coming from. Now let's talk about where the hardware trends are, because we're going to marry these together, piece these together very soon. So the hardware trends are very clear. Everything is kind of becoming larger, more efficient. Okay, so it's starting with larger, cheaper memory, larger CPU caches, larger multi-core processors, faster networks, okay? And then there's this other thing called persistent memory, really new novel memory technology, which I'll talk more about later. But if you see on the right-hand side, you see this graph that says, well, we started off with disk, and then we moved to flash, and then DRAM, and now we got persistent memory, which is really really efficient newer technology that I'll talk about in the upcoming slides. Okay, this slide talks about how Oracle has invested thousands of engineer years automating and optimizing the Oracle database. So this isn't something new to Oracle. Ever since 9i, we started looking at automatic query rewrite, right? Where we're trying to make the optimizer smarter to transform your queries to something that will run more efficiently. Automatic memory management, autonomous health framework, where we're trying to automatically diagnose your problems, right? Identify it to capture it, identify it to a known issue. So we've been doing this for decades. Okay, this is optimizing the database, but not just that, we've been optimizing the database infrastructure. Again, ever since 2008, where we started looking at smart scans, which is pushing SQL functionality down to the storage layer where the data actually resides to just send the minimum amount of data that needs to be sent back up to the compute servers. So everything from that to network resource management to supporting in-memory columnar and flash, which I'll talk about soon enough. So again, we've been optimizing the database and the database infrastructure for decades now. Now, what's new is looking at artificial intelligence trends. Okay, so with artificial intelligence trends, AI is basically penetrating all industries, right? Everything from how do we talk to our homes to turn on the lights to how do we obviously drive our cars efficiently. It's in the consumer market clearly, how to play the music that I like, etc. So AI is also moving into the database industry. And Oracle is leading this movement because of its investments in database automation, like the slides I talked about earlier. Okay, so now when you combine these three things together, you get Oracle Autonomous Database. Okay, Oracle Autonomous Database is a culmination of this complete infrastructure automation, complete database automation, and then really smart machine learning solutions to automate our data center operations. So the Oracle Autonomous Database is the industry's first autonomous database, and now I'd like to give you a little bit of a background on it. Okay, so the Oracle Autonomous Database, what and how? So first we start with provisioning. We want to be able to quickly, as you as a customer, you want to be able to quickly deploy a mission critical database. And this is done on Exadata infrastructure. Exadata, which I'll talk about later, is our database machine. Okay, it's a machine that we built with best of breed hardware that is built to run the Oracle database as efficiently as possible. So you provision a database directly on the Exadata infrastructure. Okay, database is created as a rack cluster. We have support for availability, so we create a standby system in the event that you need to fail over and transition over. So that's provisioning. Secure, we want to protect data from all external and internal threats. That means whether your data is at rest sitting in the database, we want that encrypted. If the data is coming across the network, we want that encrypted. So all data is encrypted. Manage, automate all infrastructure and database maintenance, right? So we want to use machine learning to help detect and diagnose anomalies that you might have. We want to be able to do auto patching. That's a nightmare for most customers, to be able to patch to the next release and deal with the errors that could potentially come from that. So this is all managed for you. Okay. Then there's, I'm just going to go through this: protect, scale, and optimize, so I don't have to skip through the automation slides here. Protect means, again, we want to be able to automate backup and restore. Again, if there's a failure, you want to be able to go and quickly retrieve the data that you've backed up to. Auto scaling means, every application might go through some peaks, in which case you need more CPU or need more IO resources. So we want to be able to auto scale your application when it's running on the autonomous database. So you can actually go up to 3x the CPU or 3x the IO immediately if needed, and it's a pay per use model. And then there's the optimize. If you're going to run on the cloud, we don't want you to have to tune the hundreds or thousands of parameters and events that you have. We want to be able to automatically optimize your workload based on what your workload looks like. We'll choose the right data formats, we'll choose the right access structures, choose the right plans, and select the right level of parallelism. Okay, so that's Oracle Autonomous Database in a nutshell. Now, it comes in two flavors. It comes in the Autonomous Data Warehouse flavor, which is, again, geared for data warehouse and analytics. And then it comes in the Autonomous Transaction Processing, also called ATP. And that's where you care more about transactional workloads or mixed workloads. Okay, and so we'll talk about those two flavors. If you look at this slide here, it breaks it down a little bit further. The Autonomous Data Warehouse is meant for optimizing complex SQL. Again, it's more for analytics, and so the data is stored in a columnar representation that allows you to process just those columns that you need and not the other data, but go through all the rows in a very efficient manner. We're leveraging memory for speeding up analytics like joins and aggregations. On the right side with ATP, we're really optimizing for response time. So you're quickly looking up a row in your database or some number of rows within a range in your database. And you're typically going through multiple columns across those rows. So you're interested in a row format. So you want indexes to be created to quickly access that data. You need that memory, but more for caching purposes, so that when that row comes in, it don't have to go back to disk to fetch it again. You want to keep it in that block in memory. Okay, so that's ADW and ATP. Now comes the hardware part of this. So autonomous databases run on top of the Exadata database machine that I was talking about. And what is Exadata? Okay, so as I mentioned, it is the ideal database hardware. It is built together by Oracle, excuse me, using best of breed hardware. So the fastest network cards, obviously the fastest processors. We want the NVMe drives. We want fastest network communication with RDMA. So that is the hardware configuration. We also want smart system software. So Exadata is built with smart storage software that knows how to process the data in the database very efficiently, to do things like database operations very efficiently in the storage nodes. So that's Exadata in a nutshell. And the key point I want to make is in that subtitle. It's the world's fastest database platform powered by in-memory technologies. So much of this presentation, when I talk about the top 5 transformational technologies of autonomous databases, much of that comes from the in-memory technology that we've built as part of our database in-memory solution. So I'll talk about that as well. Okay, this is just the last summary here that says, okay, the key benefits of an Oracle Autonomous Database. You want mission critical applications to run on this. So the hardware, the environment has to be rock solid. You want it to be super simple, full database automation, low risk, everything has to be secure and low cost. And so it needs to be simple to use, but it's more sophisticated under the hood. Okay, so that's now where we're going to transition over to these top 5 Oracle Autonomous Database technologies. This, by the way, is in no particular order. I just kind of went through them all here. So let's begin. Number 1 is in-memory plus Exadata. So I'm going to talk a little bit about this. The sub-bullet there is in-flash columnar processing at cloud scale. So let's get to this. First thing is something called cell memory. Now, what is cell memory? Cell memory is a technology that we have where we store hot data in the storage nodes in their flash memory, and we store them using in-memory columnar formats. Now, what are in-memory columnar formats? In-memory columnar formats are data formats that come with Oracle's database in memory option. Okay, it's the way that we transpose rows into columns for fast analytical and mixed workload processing. And we compress that data in a very efficient manner that allows us to scan that data without decompressing it, without spending too much time processing over the compressed representation. So those data formats, these in-memory columnar formats, are exactly what we use to store data on in Exadata in the flash memory on the storage nodes. Okay, and we call that cell memory. We make a distinction between cell memory and in-memory data formats because cell memory is the same data formats that we use to store data in flash. Okay, cell memory is enabled with the database in memory option on Exadata, but with Autonomous Database, it's included for free. So when you run with Autonomous Database, you are running on top of this database in memory technology without actually having to pay for that option. Okay, it's 100% automatic. So the database in memory option, it requires you to specify a size in memory for your columnar store. With Autonomous Database and with cell memory, you do not need to specify the memory size. Okay, it works seamlessly. You're running your workload, you're querying a table, it will automatically get cached in Flash using these columnar formats. Now, this is a huge advantage over other databases and storage arrays. We are basically getting an extra almost 15x columnar capacity, hundreds of terabytes on Exadata rack, just by extending in-memory processing to storage. Okay, so I'll talk more about cell memory here. Cell memory enables the same in-memory optimizations on data in Exadata Flash as on Exadata database compute nodes DRAM. So what I mean here is that all of the features that we built for database and memory option, all the analytical features, all of the mixed workload features to make your analytic workloads run faster, they carry over into cell memory. So optimized compression formats, optimized scans using SIMD technology, efficient filtering using in-memory storage indexes. The picture that I show you on the left is basically an example of how we make joins faster using vectorized techniques, okay? And you get automatic management of that data in the flash cache. So it may come in hot, it stays in the flash in flash memory, and then eventually it becomes warm and cold, and then it will automatically get evicted out. Okay? This is an example of the cell memory benefit, and this is what we call vectorized scans. So the example here is if you look at the top left, you have a table called a sales table, and the table again is stored in a columnar representation. So that means all of the state values or column values are stored together in one contiguous piece of memory. And the query that you want to run is this: find sales in state of California. So with vectorized scans, what we actually do is we leverage something called SIMD instructions, or single instruction multiple data. And how that works is the state values, they can be compressed into 6 bits to represent a state, or let's just say 1 byte. And you can load them into a CPU register, a SIMD CPU register that can actually store 512 of these states. Okay, 512 of them in one load. And then you can compare them to California, all 512 of them in one cycle. That's called a vector compare instruction. So basically in 2 cycles, one to load, one to do the comparison, you can actually get your results of all sales in the state of California for the first 512 states. Okay. In this way, we can literally process billions of rows per second. Okay. In a row store, traditional row store, you're talking about millions of rows per second. Okay, so that's one of the benefits of cell memory. And again, you're running your workload on autonomous databases, you are automatically leveraging this technology without doing anything. Okay, another benefit here, I'm not going to go too much into the details here, but the key thing is you can also offload aggregation. So if you are aggregating your billions of rows, all of those rows are stored on the storage nodes in an Exadata machine. And normally you're going to send those rows back up to the compute nodes to then do the higher level SQL operators. But we're getting smarter and smarter, and we're pushing down SQL operators down into the storage nodes close to where the data resides. And an example of this is aggregation. By pushing aggregation down to the storage nodes, what we end up sending back are not the billions of rows back, but actually a fraction of that, which represents partially aggregated rows. And then on the compute nodes, we will aggregate the partially aggregated values. So the bottom line here is that we're being smarter about the operations that we can push down into these storage nodes on Exadata. Okay, so that's all I wanted to talk about there as regards to cell memory. Again, you get it for free, okay? And it helps your analytic workloads, especially on the ADW configuration. Okay, now I want to talk about automatic indexing. So automatically create indexes based off of on your workloads. So with auto indexing, we are trying to build an expert system that basically behaves like a skilled DBA that knows how to performance tune your system and create the appropriate indexes. But we want to be able to build a system that works 24/7, that can adjust itself based off of the adjustments made in your workloads by different workloads. Okay, so it works in this incremental fashion. It's iterative and it's continuous. And we make decisions smartly. We will basically think that we should do something. We will then validate it to make sure that it was the right decision. And then we will either employ it or not. And we use this reinforcement learning to make sure we don't make the same bad mistakes. Okay, and I'll go into that here. So I want to go through each one of these steps here. So beginning with capture at the top, the first thing that we're going to do is we're going to capture your SQL workload. We're going to look at the history, see what SQL statements you've been running, what the plan looks like, what the bind values are, et cetera. We're capturing all that data. The next thing we do is we identify what are the appropriate candidate indexes that we think will improve this workload. And that's where we start leveraging machine learning techniques, machine learning algorithms to identify these potential candidate indexes. For example, you can build an index on every single column and every single combination of columns, but that would be a tremendous amount of waste of space and a huge burden on the optimizer. So we want to be smart about which columns or set of columns to create these indexes on. Next step is the verification step. We want to verify that you're going to get really good index performance. So what we do is we take those indexes, we mark them invisible so that no user query can actually use those indexes, but then we will evaluate them on the side and determine if there is indeed a performance improvement to be had on the SQL statements that we've captured. Okay. The next step is to then decide if the performance is better for all statements, mark the index visible, and now it's available for all use. If it's worse for all statements, mark it unusable, and then over time, remove that index, drop that index. And then if the performance is better only for some statements, then you can mark the index visible. But SQL statements that regress will have a SQL plan baseline created to avoid using the index. That means I want to make sure that it uses a plan that doesn't choose to use that index if it didn't show a benefit. And then the last thing is to monitor. We need to continuously monitor index usage. We want to make sure if there's any reduction in performance, we again decide whether we should have that index or not. Okay, so that's kind of high level, the steps involved for creating indexes. This is a real world performance evaluation of auto indexes. If you just look at the picture on the left, we began, this is a NetSuite ERP application. This had over 17,000 SQL statements, okay, over 1,800 tables and over 8,000 hand-tuned indexes, okay? When we used auto indexes, we got about the actually better elapsed time by just using the indexes that we created. We dropped all the secondary indexes. We created the indexes that auto indexer would have created. And the number of indexes dropped from 4,600. These are the true number of indexes that are actually used to over 1,700 indexes, okay? So we got near identical performance with a significantly less number of indexes. Okay, this slide just talks about, it's not just auto indexes, all sort of structures, access structures we want to optimize. Auto materialized views, auto zone maps, auto partitioning. And all this information, by the way, is available online. So I'm not going to go into too many details here. You're welcome to follow the links and then learn for yourself here. Okay, this is somewhat of a segue. We were talking about autonomous database features and how we're using automation to make data access structures faster. What I want to bring to your attention here is that intelligent automation expands other cloud database or Oracle cloud databases, in particular in the Exadata cloud services where we have in-memory processing, we have more intelligent automation here. So one of the things that we have is something called automatic in-memory management. And the picture that what we're trying to showcase here is in the in-memory column store, in the DRAM part where we maintain your tables and columns, it's really a store. So what that means is once you run out of space, you run out of space. It's not a cache. It's not a smart cache. So you, the DBA, would have to determine what should be in it and what shouldn't be in there. And just like what we're doing with auto indexing and all of the auto features for autonomous database, we want to be smart here. We want to be able to say, look, this table is now cold, remove it from the column store. This table is hot, bring it into the column store. And start reacting, observing the patterns, reacting quickly so that we get the workloads that are running will benefit from the tables that are in the column store at that point. Okay. Okay, number 3, converged analytics. The idea here is you want one database for all, okay? So let's go into that. Converged analytics, the motivation. So if you look on the left over here, right, you'll have a specialized database for the different data that you have. Relational database, a key value store, document store, graph database, spatial database. Your application is complex and you can either build your solution utilizing all these different data stores. And this kind of goes to my, when I talked about this initially, like you can build a smart home using a bunch of different technologies, but the reality is those technologies don't like to talk with each other. And to make them talk to each other is a very complex, expensive solution that doesn't always work. And so the key challenges here is there's no common query language. Okay, if you're writing an application that's going to talk to all five of these, six of these rather, good luck. No common set of functions. Okay, no common security model. So your main thing here is you're lacking the cohesiveness between them. Now, if you go to a single database with multiple models, which is what Oracle has, you got relational data, documents, everything is built into the database. Now you have one common query language, SQL. You have a single common security model. You have single common data masking model, single management model. And that's what the autonomous database is trying to achieve. We're saying, look, you have a single database, bring all of your data models to it, and the onus is on us to make it run efficiently. So that goes to these next set of slides. You can run Autonomous Database as a graph store. You have your vertex tables, your edge tables, they're all tables as relational tables, and you can run a PGQL language through SQL to iterate over your graph. Traverse over your graph, excuse me. Autonomous database as a spatial store. You can have spatial objects inside of this database, and then you can, we support a number of spatial functions to your heart's content that your application desires. You can have autonomous database as a document store. Okay, so I basically, the main point that I wanted to make from those slides is all of your multi-model data can reside in a single autonomous database. Now, recently, we introduced autonomous JSON database. Okay, so this is a managed cloud service for JSON storage. It's a JSON-centric cloud service. We have native JSON stores. So that means we have a very efficient data representation for JSON, something that we call OSON. We have different access methods to access the data. So you can either access your JSON documents through SQL, or you can access it through these SOTA APIs. So like if you want NoSQL-like access. And it's really more than a simple document store. It's got all of the autonomous features that you want as part of the autonomous database, full SQL support, ACID transactions, and like I said, underneath it all, it's really just an autonomous database. So if you want to promote your database to an ATP database or autonomous transaction processing database, one click and you're there, okay? So what I want to talk about, again, a little bit about the technology. This goes to what I talked about, how the JSON document, we don't just say, okay, you have access to it, it's a new cloud service. The data is actually stored very efficiently. And so we talked about the cell memory flash column store that we have. So in flash memory, we store that data, those columns, in a compressed, unique data format. And JSON is stored in this very unique OSON format that is highly compressed and very efficient to access. And so that's what this graphic here is trying to show you. Here you see the JSON document expanding out into what you can traditionally think of as a JSON document, but we store it as this binary representation. And what that allows us to do is get very good compression and like 10x performance gains when you're trying to scan, run JSON queries against it. Okay. Likewise, so not just for JSON, we store spatial objects in a very efficient representation. So if you just look at the graph, ignore the words on the left, if you look at the picture on the right in the column store here, you see that we have a column for your spatial object, but we also have some summary data that shows a bounding box of that spatial object. So now when you run a query that wants to say, is this a point in this spatial object? Am I located inside of the spatial object? I can use this spatial summary and do a very quick query to say yes or no. If you didn't have the spatial summary, it's a very complex spatial function to go through your spatial object and determine that. Okay. And lastly is text analytics. Same thing, we'll store very efficient index structure inside of the cell using cell memory formats, and then you can iterate against it or access against that text index. Okay, so that's converged analytics, number 3. Now I want to get to number 4, persistent memory. Okay, persistent memory. This is showing you a picture of Oracle Exadata. This is a new machine that came out, I think it was either earlier this year or late last year, called X8M. And on that right there is a picture of persistent memory is implemented by Intel called Intel Optane DC persistent memory. Okay, what is persistent memory? Okay, so persistent memory is new memory technology that behaves similar to DRAM. That means it's byte addressable. Okay, it's not a block store, it's byte addressable. You can get to a single byte through a pointer. The read latency is about 3x slower than DRAM, so it's not as fast as DRAM. The write latency is about 7 to 10x slower than DRAM. Okay, so far when you compare it to DRAM, you might think, oh, that's not so great. The reality of it is it's several orders of magnitude faster than flash. So if you're looking at the storage tier between flash and DRAM, PMEM or persistent memory sits very nicely in there. Its price per gigabyte is about 2x cheaper than DRAM. It has much larger capacity. So 128 gigabytes is the smallest form factor that you can get. You can go up to 512 gigabytes. Okay, and you can run it in two different modes. One mode is called App Direct mode. With App Direct mode, you're basically saying, look, leave the memory to us to directly manage. It's not part of the memory subsystem. And with memory mode, it's it's really meant for, hey, I don't want to know anything about persistent memory. I want the fastest access to it. In order to implement it, we also have a DRAM DIMM that serves as a cache that you will access first before you go to the persistent memory DIMM. And I'll talk about that a little bit in details here. So again, summarize, the benefits are, oh, I'm sorry, I forgot one very key thing. Another key thing about persistent memory is that it is durable. So that means if you have data sitting in persistent memory DIMM and then you pull the plug, right, and then you plug it back in, your data is still sitting there, accessible. Okay, there's a lot more there's a lot more sophisticated algorithms associated with it to make it durable, but that's the benefit behind persistent memory. Okay, so it's durable, it has larger capacity, and it's performant. Okay, so now the other technology I want to talk about is something called RDMA. RDMA stands for Remote Direct Memory Access. And it's network technology that allows you to directly access memory on another server. Okay, so you get high throughput, low latency network useful for distributed systems. So the picture that you see over here, I got compute server that wants to read data on the storage server. It does an RDMA, well, excuse me, the other way around here, storage server that wants to, the compute server is trying to read data off the storage server. So it does this RDMA read. And the way it works is that the server will create this protection domain, and it will identify very specific memory regions that the compute server can access. And the benefit of RDMA is it bypasses the operating system completely. So there's no, for example, context switches that are needed. You can directly read that memory and bring it back in. Okay, so focused really on low latency reads. Now, I'm going to skip this slide and just kind of go to how it's actually used. So persistent memory is available on the Exadata X8M systems that are now available on the Exadata Cloud services. And the picture on the left shows how it's being used. You see this compute server, and it wants to read data on the storage server. And persistent memory here is used as a cache. So your hot data is sitting in these PMEM DIMMs. And then you got flash, which is for your warm data, and you have disk for your cold data. And so the first thing it's going to do is it's going to try to read that data on the persistent memory DIMM. And it's going to, like I've said, bypass the operating system on both sides completely. So it does this RDMA read to try to read or fetch that row directly. And when it does that, latency is about 10x faster, okay, 10x faster using RDMA. And in X8M, we're using RDMA over converged Ethernet, so we're getting about 100 gigabits per second, and that's what's giving us this very fast latency. Okay. Okay, so last thing I want to talk about here with persistent memory. So I talked about this app direct mode where we are managing that persistent memory directly. In memory mode, there's nothing to do. There's literally nothing to do. So the example I like to give here is today, imagine you want to run your workload using the database in memory option. You want to put all your data inside of a column store, so you can run analytics fast. Okay. To do that, your column store you can only size the column store to however much memory you have available. And so more likely than not all of your data can fit into memory. And so what happens is that when you run your query, it's going to go against the column store as much as possible, but then it has to go against the row store on disk, right? And that's the situation that you have. Now, DRAM DIMMs also, as I mentioned, they can go up to 128 gigabytes, but they're very expensive. So you can buy more, but it's very expensive, and then you're still limited. Now, that's today, okay? If you're using Intel Optane DC persistent memory, you can, as I mentioned, run in this memory mode. Now, with memory mode, your hottest tables are actually cached in DRAM, okay? And so you're gonna go to DRAM, to that volatile memory, to try to get it. And if it's not there, then you go to the persistent memory DIMM. And again, if you're constantly going to the persistent memory DIMM, as we mentioned, it's about a 3x, it's 3x slow. The latency is about 3x slow to fetch that data. So the cache in DRAM has to be very efficient. And we found it to be very efficient, especially for an analytic workload where you do have hot data, warm data, cold data in your life cycle, in your workload life cycle. So here, now you can imagine your entire workload can fit into memory, into persistent memory in particular. Okay. Now, when you do that, by the way, I'll get to the performance here. The last slide here is talking about when you're running with some of those vectorized solutions I talked about. In this case, we have a feature called deep vectorization that makes join processing faster. You can get even more performance. So this is a demo that we did as part of the Oracle Open World Conference in 2019. And what we showed on the left here was DRAM configured at 384 gigabytes. And we ran a very complex query, an analytic query that had joins and scans and aggregation. And you can see that we processed over 18 billion rows. Okay, and we did that about 130 seconds. And this is the configuration where not all of the data could fit in DRAM. Okay, then we went to memory mode, where now we have 1.5 terabytes of data. And just like that, everything could fit in 1.5 terabytes. And we immediately get about 10x faster performance because everything is running against either the DRAM cache with memory mode or through the persistent memory DIMM. And then the last thing is when we use those vectorized features that I talked about in combination with memory mode and everything fits in, we can get an additional 4x faster performance. So now we're about 40x faster than the baseline. Okay, so the technology is amazing. Okay, persistent memory technology is definitely a game changer. It gives you that capacity, it gives you that durability, and yes, latency is a little bit slower, but if you run it with memory mode, you get good performance. Okay, so last thing I want to talk about is as it relates to transformational technologies with autonomous database is auto space management. Okay, and you can generalize this to just resource management in general. Okay, if you're running on the cloud using automation, there's a whole bunch of things going on in the background to make sure that the system is running smoothly, especially if you're on a multi-tenant system where you're sharing the Exadata infrastructure with multiple tenants. You want to make sure that that everything's running smoothly. Okay, so auto space management. So automatic space management, database queries can result in significant space being allocated for temporary operations. So if you're running a complex analytic query that has lots of joins in it, joins take up a lot of space because you have to build these intermediate structures that first we will attempt to allocate them in memory, but if memory is not big enough, we need to spill over and allocate data from disk. And that's what we call in that example is our temp space, okay? Now, if this allocated temporary space can be efficiently reused from subsequent queries, no problem. I don't have to allocate that space again. I'll just reuse that space, okay? But if there are no queries that are using that much space, that space just stays allocated. And if you're running on the cloud, you're paying for those resources, right? So we don't want you to have to pay for resources that you're not actually using. So we want to be able to shrink that space. Now, you can shrink that space manually, but with autonomous, again, we're done with manual intervention. We want everything to be smart. We want to do it automatically, okay? So there are two types of table spaces that we're looking at. One is the temp table space, which I kind of talked about, these big memory SQL operators like hash joins, sorts, order by, indexing. They require a lot of memory, okay? And then there's undo table space, which I'll talk about next. So that's temp table space. We want to automatically shrink and extend the temp table space. So like we can shrink that space, but then if we all of a sudden a query comes in that demands that memory again, we don't want that query to stall and spend all of our time allocating space on disk before that query can run. So we have to be smart. We have to be able to predict based on looking at the space trends when we need to extend preemptively so that that query, when it comes, will benefit from it, okay? With undo table space, so undo space keeps data that's needed for transactions to roll back. So if you have a transaction that's ongoing and all of a sudden you need to roll back that transaction, you need to know how to get back to the state that where you were. And we store that data in this undo space. Now, that space has to be kept around until this undo retention period expires, okay? Or until that transaction commits. Now, in autonomous database, there's a limit on how big that space can be. That's 5% of your overall space. Okay, transactions start to fail after they hit that 5% limit. Okay, and so same solution, same technology. We want to be able to shrink that space when we don't have a lot of concurrent transactions that are running. We can afford to shrink that space, save on that resource. We want to be able to make sure that we can grow efficiently when we start having a lot more transactions coming in. Okay, I think that's all I wanted to say here. I had some more detailed slides, but I was a little bit afraid of going over my time. So I want to go ahead and just summarize now. So the top 5 innovations summary here. Again, this is a nice picture here that breaks down Oracle Cloud. So Oracle Cloud, you can break it down to left on autonomous databases, and then on the right is our co-managed database services, okay? So going to the co-managed database services first, we have specialized high performance services like the Exadata cloud services where you really care about scale, performance, availability, and you want more hands-on, but you want more hands-on to control your environment. And the same thing with DBCS or database cloud services. There, you get yourself a VM or bare server, and you can have one node or you can have multiple nodes in a rack cluster. That's co-managed. What we've been talking about is autonomous database. So all database operations fully automated. User runs SQL, no access to the operating system or the consolidated database that's for multi-tenant. And then you have two different flavors there, which I didn't talk about at the time, shared versus dedicated. Shared is a multi-tenant environment where you're basically sharing the system with multiple tenants. Super simple, very elastic, auto scale, all of that. Dedicated is you basically get your own, Exadata environment, but you have some customizable options within this environment. Okay, so that's autonomous database. This slide kind of shows the stack. So at the bottom, you begin with Oracle database, the world's best database, runs anywhere, and then we bring that into Exadata, which is the the world's best database machine, right? And then we start using that technology in the Oracle Database Cloud Services. We want the world's best database to run on the world's best database platform, and we want to build cloud services around that. And now we bring that into autonomous databases for fully self-driving database. Okay. This slide here, talks to how analysts view our solutions, okay? So this is in 2019, a Forrester Wave translytical data platforms. Translytical workloads basically means a mixed workload where you care about not just analytics, but also transactions in a mixed workload environment. And so you can see Forrester ranked Oracle as the leader. Both, we have strong strategy, we have strong current offering. So they ranked us high on both axes. And these are some of the quotes that they've given. And I like to call out some of this, like this dual format database. This is a technology that the database in memory option is built on, where it's built so that you can run mixed workloads very efficiently. Multi-model, which we talked about in the Converge Analytics this section, do not require any changes. That's, again, really autonomous. That's all autonomous database talking there. Okay. Lastly, we got thousands of autonomous database customers. There's the splash slide there. And the last slide here, always free. You can go to this link, oracle.com/cloud/free. You can get a free configuration here, an autonomous database. You get 2 databases, each one with 20 gigabytes of storage, compute, some 2 VMs for compute. You got some additional storage there for your applications and some networking restrictions there as well. Okay. And with that, that's it.
Thanks for the talk. Thanks everyone for attending. And the conference begins at 7:30 a.m. Pacific time tomorrow with the first breakout sessions. Hope to see you then. Thanks everybody.
Great, thank you so much.